Hello, everybody. Welcome back. Today we're going to be starting a new unit. It is the last unit in the AP Chemistry curriculum, Unit 9, which is all about the applications of thermodynamics. Today we're going to be looking at subunit 9.1, which introduces us to the concept of entropy, which you may or may not have ever heard of before. So let's get started. So if you've been following my videos, I always start a new unit with a little factoid, and I always think this is so interesting because there is little to no gravity out in space, the spine expands, and people actually come back to Earth a little bit taller. Now, of course, they don't stay that way, but I just think that fact is interesting. So, as I said, we're starting a new unit today. And one of the things that is a major topic in all of Unit 9 is predicting whether a chemical reaction will be spontaneous or not. And thermodynamics is a concept that is going to help us make that determination. And instead of using the term spontaneous, the AP exam prefers that we use the term, and it's a very wordy term, thermodynamically favored. Meaning, is this a chemical reaction that will occur without any outside intervention? Is it one that you put the reactants together and they just go on their own? They go and they produce products without any help from you or anything else. All right, just as an example, okay, if you release a ball at the top of a hill, it will spontaneously, on its own, roll down that hill. A ball, if it's sitting at rest, is not going to spontaneously roll up a hill. The only way you can get an object to move up a hill is by applying a force, expending energy. And those are expending energy. That's something we're going to talk about in this unit. But one of the big concepts, again, in Unit 9, is being given information about a particular process, and we are asked to predict or prove whether this process will be thermodynamically favored or not. One of the tools we're going to use to help us make that determination is the concept of entropy. So, ladies and gentlemen, entropy is abbreviated with a variable, a capital S. And let's define it. Entropy is randomness, disorder, chaos, messiness, okay? And certain states of matter have more disorder than others. For example, think way back to earlier in this AP Chem curriculum this year. Think about the structure of solids, any kind of solid, okay? They have a typically very organized pattern. The atoms and molecules are very close to each other. There's very little movement, whereas liquids have some connections to each other, but there's not as much structure, there's more movement, and of course gases have little to no forces exerted on each other. They're moving at high rates of speed, there's lots of disorder. So in general, ladies and gentlemen, the entropy of a gas is much greater than the entropy of a liquid, which will thus be greater than the entropy, the disorder of a solid. Solids have the least amount of entropy. Okay, and as I said, we're going to use the concept of entropy to help us predict whether a process will be thermodynamically favored. And most, not all, most thermodynamically favored processes show an increase in entropy. okay? The way that the universe works, ladies and gentlemen, is that processes tend to increase their entropy. And the example I always give my students is if you imagine the state of what your bedroom, your room would look like over the course of a month, if you never expended any energy to clean things up, you never put your clothes away, you never cleaned things off of your desk, you never made your bed, you never even threw things away in the trash can. I mean, I know that's kind of gross, but you know, you use a tissue to blow your nose, you just drop it on the floor. If you expended very little energy, the entropy of your bedroom would increase dramatically over the course of time. That's just sort of how things tend to go in nature, in the universe. And we'll talk a little bit more about that in a minute. But one of the things that you are often asked to do, particularly in multiple choice, is being given a particular process and being asked to predict the change, predict the sign, positive or negative, for delta S. Okay, so let me just make sure we understand what we're talking about. So delta S would be the change in entropy. So for each process, you want to ask yourself, is the disorder increasing or decreasing? Are things becoming more chaotic? If that is the case, then delta S will be positive. Whereas if in the process things are becoming more organized, then delta S will be negative. Some of these are just simple phase changes. Others are chemical reactions. So we're just going to talk through these together. So imagine you take a cube of sugar and you dissolve it in hot tea. Think about, is this process becoming more organized or more disordered? Hopefully you said more disordered, because that sugar cube is going to break up, it's going to dissolve. So delta S will be positive. Entropy is increasing. The next one says a lake freezes over in the winter. Think about what phase change that is. Liquid to solid. Think about what we said in terms of entropy of solids and liquids. This is a situation where the particles are becoming more organized. So that's going to be a negative delta S. Rainwater on the pavement evaporates. Think about phase changes again. Evaporation. Liquid to gas. Is that becoming more organized or more chaotic? It's becoming more disordered, liquid to gas. So it's going to be positive. Okay, now let's look at some chemical reactions, and you can still look at states of matter. That's always something to look at. But another something to consider, guys, is like, for example, in this next one, two reactants are becoming one product. Two things are becoming one. That is just by itself a synthesis reaction, not always, but is very often a situation where things are becoming more organized. And then to reaffirm that, look at the states of matter. We have solid lead, gaseous oxygen, that's on the reactant side. And then on the product side, we have one thing, and that one thing is a very organized solid. This chemical reaction is an example where the entropy is definitely decreasing. So delta S will be negative. Okay, now in the next one, if you look at the states of matter, everything is a gas. Okay, so you can't necessarily use, there's no phase change going on. We're not changing states of matter here. But you can use kind of two arguments for this one. All right, once again, this is a synthesis reaction. Okay, two reactants are becoming one, so it's probably a situation where things are becoming more organized, but here's another reason. Okay, look at your coefficients here. You have 3 moles of gas on the left and only 1 mole of gas on the right. Remember, gases have a high degree of entropy, so there's more gas on the left, less gas on the right. That's another argument you could use to say that this is becoming more organized. Entropy is definitely decreasing. Okay, last one. We have solid copper chloride dissolving, okay, into its aqueous state. This is essentially writing out the chemical process of this one. I mean, this is showing an ionic compound. This example here is showing an ionic compound dissolving. So think about it. Does the process of dissolving anything, is that becoming more organized or more disordered? It's becoming more disordered. So it's a positive delta S. So you'll very often be asked to make these predictions. If it's in free response, you'll be asked to defend your answer, okay? Explain your reasoning. All right. So let's look at a practice free response question. You're given what's called a heating curve. It says at 1 atmosphere, a sample of ice is heated to liquid water and then to water vapor. We have seen these graphs before. If you need to go back in your notes and figure out what's going on at each part, please do that. The heating curve is shown in the graph above. Predict the signs for the change in enthalpy. Ladies and gentlemen, let's review. This word right here, that is the same thing as heat energy, delta H. Okay, we saw that back in Unit 6. Okay, predict the sign for delta H and delta S for the process corresponding to what's going on there, segment X, going from left to right, and justify your answer. So pause the video, see how you do. Okay, let's just refresh your memory on what is even going on in this section up here. Okay, in a heating curve, remember that the flat plateau areas are where a phase change is taking place, and what's going on in segment X is liquid to gas, vaporization, boiling. Okay, so here's what I said for my answers. The enthalpy, delta H, is going to be positive because vaporization, liquid to gas, is an endothermic process. Heat is required, and that means a positive delta H. For the second part, the entropy change, I said, is also positive because a phase change from liquid to gas is an increase in disorder. Okay, so sometimes you can see questions that bring those two concepts together. We're going to see that more and more throughout this unit. Okay, the last thing that I just want to say is that, and I sort of hinted at this before, one of the things, again, that you're going to be asked to either predict or prove in this unit frequently is a process thermodynamically favored, spontaneous, or not? And entropy is one of the tools we will use to help us make that prediction. If the delta S of the particular process you're looking at is positive, okay, now let's stop there. A positive delta S, what does that mean? The process is becoming more disordered. That is usually, notice it says the word usually, not always, that is usually going to indicate a thermodynamically favored process. If the delta S is negative, that's usually going to indicate that this process is not thermodynamically favored. However, if we looked at the reaction in the opposite direction, that direction would probably be favored. But we're going to touch on that whole concept of is it favored or not in a later subunit. So that's it for talking about entropy. I hope you have learned a little something today, and I look forward to seeing you next time.